Hello. So this is the MobilityFirst project, and this is a poster and demonstration about one of the components of the MobilityFirst architecture and protocol. So MobilityFirst is a clean slate architecture project to address challenges of the future internet, mainly mobility, and how do you track mobility, how do you address things like bad link qualities, variable link qualities, and also disconnections at the access networks. So one of the main components in MobilityFirst is a global directory service which tracks the IDs of the network entities and their network addresses. So whenever a communication is required between two mobile devices or between a static device and a mobile device, you can always look up the resolution service to determine the latest location of the network entity. So the poster here essentially shows the GNRS component, which is primarily being demonstrated here. And what we're doing is to enable a scalable GUID to NA, where the GUID is the ID of the network entity and NA is the network address of the network entity at any point in time. We use a global name resolution service, which is a distributed service implemented within the network using a direct hashing scheme. So the direct hashing scheme works like this. Essentially, whenever you want to resolve a particular GUID to a network address, you consult the service, and the service determines where the GUID to NA mapping is located within the network and retrieves the mapping from there, and the routing can proceed from that direction. So in order to have replication for both availability and performance, we can use multiple hash functions to determine where these mappings reside within the network. And the more the number of hash functions, the more the number of locations, which gives you a choice as to where to retrieve the mapping from, which could improve the performance significantly in terms of the latency that you incur to retrieve the mappings. So the graph over here basically shows that as you use more number of hash functions, you could reduce the amount of latency incurred in retrieving the mapping. So with a number of hash functions equal to 5, you could actually reduce the latency of retrieval of the mapping to around 80 milliseconds, which gives you a good number for being able to support real-time applications in high mobility conditions. So in the demonstration and poster that is presented here, what we're showing is we've deployed the components of the MobilityFirst architecture, including the global name resolution service and MobilityFirst routers, both on GENI as well as the Orbit testbed infrastructure. And one of the things that we want to evaluate is how the architecture performs as you introduce mobility events. So if you look at the figure over here, essentially what we're trying to do is emulate some of the mobility events that the architecture will incur as users move through the network and encounter different access points, be it Wi-Fi, cellular, or WiMAX access points. So in this scenario, the user moves from home to work and actually encounters multiple access points, Wi-Fi access points and WiMAX access points. And what we're trying to do is essentially map this mobility scenario onto a protogeny and mesoscale deployment of the MobilityFirst architecture. So we're deploying multiple MobilityFirst routers within the core of the GENI protogeny deployment. And we are deploying the Wi-Fi access technologies at the Rutgers edge, wherein we can have the real mobile user move through a region wherein the coverage of the Wi-Fi and the WiMAX access points varies. So as the user moves through different coverage areas, he will be able to connect to different networks, which is Wi-Fi or WiMAX. And accordingly, the point of attachment is reported to the GNRS, the Global Name Resolution Service. And whenever packets need to be delivered to the client, the routing fabric can actually consult the GNRS to do the delivery according to the latest location of the user. So in the demonstration that we have today, essentially what we've done is an emulation of the mobility scenario. And the figure over here shows the Orbit or rather the WinLab building, wherein a user moves through the WinLab building and accesses different access points, Wi-Fi access points, as he moves through the area of the building. So the signal strength of the access points varies, from one point to another, and at any point in time, the best access point or the set of best access points varies, as the user moves. So essentially, what we do is we emulate this scenario by using a sandbox within Orbit, which gives us the ability to replay the trace that we gathered, wherein the user encountered different access points, and created a similar scenario wherein the received signal strength from our deployment varies for the user. So, quickly switching to the GNRS component, which is actually tracking the location of the user as he moves through the network, you can see the mappings of the GUID to network address that is being stored at different nodes within the deployment. So, so taking a snapshot of one of the mappings, what we see are 4 fields, essentially. The first field being the GUID, which is the identity of the network entity. The locator is the actual network address that the entity is currently connected at. And expires at gives you an idea of how long ago the user or the entity was seen at that particular network location. So as you can see, we are replaying the trace as the user moves through the WinLab building, and he attaches to different access points, and the GNRS is essentially able to capture this, and which can then later be used by the routing fabric to deliver packets to the user at the appropriate access point attachment. So that is the basic demo, and the GNRS component is the primary component that we're trying to show here. We have other demonstrations, and we've done a previous demonstration at the GEC plenary session. And in the future, we would want to do larger scale deployments of the MobilityFirst architecture and do real evaluations using opt-in users to drive the traffic through the network. Thank you.